Let's start by defining a special number that we call Euler's number, and we use a lowercase e to denote this particular number. It's a really odd number in the sense that it's defined as what we call a limit. So we look at the expression 1 plus 1 over n to the power of n. And as we allow n to get really, really big, so that means as we allow n to go towards infinity, this particular expression tends towards some number that we call Euler's number. To give you a rough idea of what the value of e is, let's try to substitute some numbers into this formula. Let's begin with the number n is equal to 1. If we substitute n is equal to 1, we're going to get 1 plus 1 to the power of 1. And this is equal to 2. Next, we might try n is equal to 10. And from here, we may want to pull out our calculator because we're going to have to deal with that fraction and that exponent. And if we use our calculator, we should get a value that's roughly equal to 2.5937. Now we could make the value of n even bigger. We could try next a value of 1,000. And once again, you could try plugging this into your calculator. And in this case, we get a number that's roughly 2.7169. And I'm going to choose a really large value next. I'm going to choose the value of 1 million. And if we were to substitute that into our expression, we would get roughly the number 2.71828. So you can see that as the values of n are getting larger and larger, the right-hand side is actually tending towards roughly 2.71. And that is about what Euler's number is. So let's just write that in here. E is pretty close to the number 2.71. Now, based on what we saw earlier, it's not really immediately obvious why we care about such a number like Euler's number. This is something I really can't motivate in pre-calculus, but it does become a bit more apparent in calculus. It turns out that this number just happens to be the best choice as the base for an exponential function. Since e is roughly equal to 2.71, it's a real number, and we can define an exponential function as follows. We might say the natural exponential function is called e to the x. So here we take that special number called Euler's number and we use it as the base of our exponential function. This leads us to the following definition of the natural exponential function. Like we said on the last slide, if we decide to use the base e for our exponential function, we get the natural exponential function, which we call f of x equals to e to the x. Since e is a real number, when we make the substitution of x is equal to 0 into this particular function, we're going to get the number 1. So the point 0, 1 is always going to be on the curve e to the x, and it's going to increase as we move right, just like our usual exponential functions, and it's going to decrease as we move to the left and get closer and closer to the horizontal asymptote of y is equal to 0. So as you might be able to see from the graph of e to the x, the domain of this function is going to be all real values. That is, x is allowed to be on the interval negative infinity to positive infinity. In this example, I want to graph three functions on the same set of axes for you. I want to graph the exponential functions 2 to the x, 3 to the x, and our new natural exponential function e to the x. So remember that our exponential functions will pass through the point 0, 1. So I'm going to go ahead and I'm going to put that point in here, 0, 1. And all three of our exponential functions are going to pass through this particular point. First, I'm going to graph 2 to the x. Remember that as we move to the right, our exponential functions are going to grow exponentially, and as we move to the left, we're getting closer and closer to that horizontal asymptote of y is equal to 0. Next, in blue, I'm going to plot the exponential function 3 to the x. So again, it's going to pass through this point 0, 1. But 3 to the x, because its base is bigger, is going to grow much faster than the exponential function 2 to the x. And as we move over to the left side, it's going to decrease much faster than 2 to the x as well. Finally, in green, I'll show you what the exponential function is going to look like. Remember that the base e is roughly equal to 2.71. So once again, it'll pass through the point 0, 1 here. And it's going to land somewhere in between these two exponential functions, but it's going to be a bit closer to the exponential function 3 to the x. So e to the x is going to look something like this over on the right-hand side. It's going to grow a bit faster than 2 to the x, but not grow quite as fast as 3 to the x. And then over on the left-hand side, again, it's going to decrease fairly quickly, but stay in between 2 to the x and 3 to the x. In our last example, we want to take the graph of f of x equals e to the x and use that graph to give a rough sketch of the new function negative e to the x. So on the left here, I've plotted the function f of x equals e to the x. So you see I've included the point 0, 1. This is a point that's on every exponential function. And I've also included the horizontal asymptote at y is equal to 0. Now what we might want to do is we might want to consider what does this negative sign mean in our function g of x. Well, this negative sign is going to have the effect of changing all of our y values from positive numbers to negative numbers. So in effect, this is going to reflect our original graph over the x-axis. So that means that our horizontal asymptote is going to stay at y is equal to 0. However, our point 0, 1 is going to be reflected over this axis, and it's going to come down here, and we are going to get 0, negative 1. Now let's take a look at just this section of our exponential function. This is the decreasing section. We're going to flip all of our y values over the x-axis so that we have a picture that looks like this. So again, over on the left-hand side, we're getting closer and closer to our horizontal asymptote. And then finally, we'll take this side over here on the right. We're going to negate all of our y values or flip them over the x-axis to get our remaining piece that looks like this. All right, my little epsilons, stay positive.